All right, so the second part of our spring break notes that we're going to be doing is separable differential equations, which you've already seen an example to us. We're just going to basically go through several more examples. The general technique is for your textbook is going to be in actually section 6.2, and then we're going to have some applications that we're going to look at exponential growth and decay in 6.3. Now, what we've done in the AB class is we've looked at it from the graphical, i.e. slope fields method of solving your differential equations. We do not do the Euler's method, which is the numeric method. That's a BC topic, so we're going to skip over that. And so now we're just going to do a bunch of practice doing the algebra of separating and then finding the antiderivatives. One of the key things about this is you're basically trying to separate all the x's and dx's onto one side of the equation, all the y's and dy's onto the other. For some of the equations, it's not possible. That's why they have a whole class called differential equations, or diffie-q, as it's fondly called, where they will do techniques for non-separable differential equations. But all you are required to do in the AB class is to do the ones that are separable. And the key thing, one thing that you must remember whenever you are in a free response problem, you must show the separation of the variables. If you do not show that, you will not get credit for doing the separation. Okay? So just as an example, let's take a look at example 1. I have a graph of several solutions over here to the differential equation, and we're going to solve the equation analytically, and then we're going to find 3 particular solutions that satisfy these 3 different initial conditions. All right, so I'm going to start here. I'm going to take my dy dx, which is equal to x squared over y squared. And step 1 is to always separate your dx's and your x's and your y's and your dy's. And in general, anytime it's multiplication division here, it's always separable. I'm going to move the y squared over by multiplying, and then I'm going to move the dx over by multiplying. So you must show this step. This is the step that separates or is saying that we have a separable differential equation, and you must show this step. They must see that on your paper. The next thing you do, you can go ahead and put in your integration symbol here and here. That's perfectly okay to have that written on that line. You still show that you separated. Now we're actually going to take the antiderivative. The antiderivative of y squared would be 1/3 y cubed. Now generally we would do plus c here, but this is the idea of where if I had plus, say, c1 here, I'd also have a plus c2 here. And in the constant world of these problems, we kind of go, I would just subtract this over anyway, combine it with that. And so the idea is we're just going to have a constant. It doesn't really matter that we have it split from one side to the other. So in general, we go straight from here to just putting 1/3 y cubed equals 1/3 x cubed plus c. We call it the mega constant. Yes, it's a combination of both of these, but we don't care. We just know there's a constant added. All right, so we get to here, and that satisfies the general solution to your separable differential equation. I'm just going to abbreviate that as diffie-q. Now we need to find our particular solution. So the first particular solution, we need y of 0 to equal 2. So essentially you just have to find the constant. If I put in 0 for x and 2 for y. Now I will say, kind of before I do this, I might want to come in. A lot of times when you have your general solution, they do prefer it solved for y. So a lot of times we'll come in and we'll keep going and we'll do y cubed equals x cubed plus, oh yeah, it would be 3c, but again, we're just going to call it the mega c that's going to take care of everything. And then I'm going to take the cube root, and so y equals the cube root of x cubed plus c. So this is in general kind of the format. You usually find your general and then solve for y and get that in terms like this would be your general solution. Now I'm going to go ahead and do my initial condition, y of 0 equals 2. So if I plug in 0, I get the cube root of c is equal to 2, so c would be 8. So my particular solution in this case would be y equals cube root of x cubed plus 8. And then that would be my version for the first one. Now for the second example that we had, in that case we had y of 0 equals negative 2. And hopefully you'll be like, hey, that's really not that much different. So negative 2 equals the cube root of c, so c equals negative 8. So the particular solution here would be y equal to cube root of x cubed minus 8. And then for part C, we had our initial condition was y of 0 is equal to 0, which essentially is just going to make c equal to 0. So our particular solution would be y equals the cube root of x cubed. Oh, wait a minute, that is my y equal to x. And what you see here, and this is kind of a good thing to kind of go back and look at, what is the effect of the constant that's there? Notice that this constant is inside of our function, the cube root, when you solve for it, because it was this mega constant and then I had to solve for y. And so because of that, it's not just a vertical shift anymore. What you see is the constant is affecting it in this fashion. Here's my y equals x, and then you can kind of go, well, the one that goes through 0, 2 would be this one right here coming across, and then the one that's 0, negative 2 would be, oops, let me undo that. That would be this particular solution. So the idea is the constant, they're only different by a constant, but because the constant was inside of a function when you solved it for y, it's no longer just a vertical shift of each other. Okay, so that way you can kind of see the effect that the constant, the difference that you see because of the constant, how it's not just a vertical translation anymore because it happens to be inside of a function. All right, let's take a look at the next example that we have. And that's pretty much what this set of notes is. It's just going through some examples and giving you a little extra practice on these separable ones. All right, so I want to find the general and particular solutions to the separable differential equation, x squared times y. And again, you notice that it's got an x squared and a y, and it's multiplied, so that's going to be easy to separate. Generally, when you have addition in between your two terms is when you can't separate. So we're going to go ahead and we're going to show the separation. I'm just going to come down here and just separate. I'm going to divide by y, which is going to give me 1 over y dy. And I'm going to multiply by dx, which gives me x squared dx. And so there's my step where I have shown the separation, and I add my integral symbols to show I'm going to take the antiderivative. The antiderivative of 1 over y is natural log absolute value of y, and 1/3 x cubed. I'll put the plus c over on this side. Now, I am going to talk a little bit about this in that this was actually one of the ones that was on the prior notes with the slope fields. And I kind of did it a different way in the actual key to that set of notes. Here, I'm going to actually solve for y before I find a particular solution. Because really what you're going to do is you're going to basically do e to basically raise both sides to the e because it's the inverse, right? And so little algebra, that's going to then cancel this out. Absolute value of y equals e to the 1/3 x cubed plus c, okay? Now, there's a little bit of math here, but I'm going to show you this and then we're pretty much just going to accept it and see how this works. First off, e to a power is always positive, so you no longer need your absolute value, so take that out. And then over here, when you have addition in your exponent, that's the same as e to the 1/3 x cubed times e to the c. And when you separate it in this fashion by using your exponent rule, you really recognize that this part right here is nothing more than a constant. And just like we were absorbing constants and making mega constants in the previous example, I'm just going to call that c. All right? So we're essentially going to end up with a general solution, I'll put that here, a general solution of y equals c e to the 1/3 x cubed. And that's going to be the general solution that I'm going to use. Okay, and then we'll go to part 2, which is fine given these initial conditions. Okay, let's kind of separate this out here, give myself a little room. So when f of 0 equals -2, then we pretty much know, well, e to the 0 is 1, so c equals -2. It actually makes it really easy to solve for c. So your particular solution in that case is going to be y equals -2e to the 1/3 x cubed. And that would be your particular solution for that one. And so here's my 0, -2 point. And so the idea is, what does this look like? And because it's got this little x cubed in, if you follow your path, follow the flow, that it probably has something along these lines and then coming this way and coming down. And if you were to graph this, you would kind of see the behavior that's going on with that. And then our final one, when f of 0 equals 1, okay, and in that case, if I plug in 0 and I get a 1, so c equals 1 in that problem. So my particular solution is going to be my y equals e to the 1/3 x cubed. Okay, and you could draw that one on. You can take a look at the graph on your calculator and see how that works. But again, these are pretty straightforward problems that you're going to be working on. All right, let's take a look at another AP example. So I'm giving you a function with an initial condition, and the slope is given by this. And I want to find the slope of the graph at the point where x equals 1. Well, notice that in order to find this, I have to know y. So you might go ahead and calculate, oh, look, f of 1 equals 4. So when x is 1, we're basically looking at the point 1, 4. So we basically want to find the slope when x is 1 and y is 4, and you just show your work for that. 1 squared plus 1 over 2 times 4, nothing but plug and chug. 3 plus 1 is 4. 4 divided by 8 is 1/2. All right, so A, pretty easy. Nothing more than recognizing you have to have an x and a y. All right, for part B, we want to write the equation of the line tangent to the graph at x equal to 1, and then use it to approximate f of 1.2. So you're starting to see a trend in some of the things that they've had. We had an example similar to this in the last note. So for B, our tangent line equation is our slope is 1/2, and this is at the point 1, 4. Okay, so make sure I say where I'm at. So it's 1/2 x minus 1 plus 4. My point, 1, 4, my slope, 1/2, which I calculated in A. And then we want to use that to approximate f of 1.2. So we want to show that f of 1.2 is approximately, remember this is called your linearization of the line. You can do your L of 1.2, but in general you pretty much, as long as you don't even have to call it the linearization. And I always do that. I always hit that reset button instead of the go back button, which is what I was trying to do. All right, so what you're basically going to do here is you can basically go, I can estimate f of 1.2, okay, and make sure we've named this. They named it f of x, so we're fine on that. So f of 1.2 is going to be approximately, you can just go ahead and plug in your 1.2. You can leave it at that, but it's okay to simplify. This is pretty easy. You basically have half of 0.2, which is 0.1, which is 4.1. Okay, so that's going to be our estimate. And they did not ask me about over or under estimate, so I'm going to move on to part C. Find the function by solving the separable differential equation with that initial condition. So I show the separation, that has to come first. So 2y dy equals my 3x squared plus 1 dx. So that's the showing the separation. Go ahead and put your integral symbols in to show what you're going to do. And so you have to have that step in there to get credit for separating. Okay. Now I'm going to take the antiderivative. The antiderivative of 2y is y squared Don't worry about the constant. We're going to absorb it to the other side. Antiderivative of 3x squared is going to be x cubed plus x, and then plus the c that we have. And then we want to say when f of 1 equals 4, reference your initial condition, we will end up with 16 equals 2 plus c, or c equals 14. Okay. And then we want to write down our answer, which, because you got to make sure you answer the question. So f of x, our particular solution is going to be, oh, what should I do here? I went ahead and found c simply by solving this. I need to actually go y equals plus or minus the square root of x cubed plus x plus 14. That's my particular solution, but you're going to wait before you say that which one do you have. All right, let me pause. Okay, sorry, a little interrupt with the phone call there. Once you get to here, remember this is the plus or minus that really is in the general, and you got to look at what point you went through. I went through 1, 4, so you have to choose when you go to the particular solution whether you're on the plus or the minus version of that. Now the easiest way to do that is to simply plug in. If I plug in 1, I get square root of 16, and I want positive 4, not negative 4, because of here. So I really just want to go, it's the square root of x cubed plus x plus 14. So that way you got to make sure you can leave the plus or minus in the general solution, but you need to take out the one that is not the one you want for the particular solution. So you can leave your general solution here. You can make your general solution plus or minus with the c in it. But once you go to the particular solution, you have to pick the one that is appropriate for the point that you have. So I just wanted to emphasize that. And then in part D, use your solution to find f of 1.2. So again, very similar to what we just did in the previous set of notes. Your f of 1.2, I can actually use my formula here, which is cube root of 1.2 cubed plus 1.2 plus 14. Okay, and that's pretty much it. You don't have to simplify. If you had a calculator, I don't know if this was a calculator problem. I don't think so, because it's number 4 in the list. So at that point, you just pretty much had to say, hey, there it is, and then walk away from it. Okay. All right, so let's take a look at, and was that the last thing I had to do? A, B, C, and D. Done. All right, so let's go to the next one. Now we're going to get into some applications. This is called the law of exponential change. And this is just basically, this is a classic problem that with exponential growth problems, that anytime you have exponential growth, the rate of change of the quantity that you have is going to be directly proportional to the quantity itself. It's like going back to Algebra 2, where you have your direct variation problems. But it's your rate of change, your slope, is proportional to whatever the quantity is, which is y. So we end up with basically a differential equation. So let's take a look down here at example 4 and go for solving the separable differential equation. So step number 1, you want to separate. And so notice k is a constant here. So there's no t in the problem, so you pretty much just need to get the y with the dy. So I'm going to divide the y over and make it k dt. Remember, a constant. And then we're going to integrate, put our little integral symbols in. We're going to have natural log of absolute value of y, again plus c, but we're going to add that to the other side. And the antiderivative of a constant would be kt, and then plus the constant of integration. So that gets us to here, and usually at this point we want to solve for y. You're not going to leave it at this point. So you're always going to pretty much come up here and you are going to solve for y. And again, to solve this one for y, we're going to raise both sides or add an e. Here, the reason we do that is so that would cancel. Absolute value of y equals e to the kt plus c. And then again, absolute value, not necessary because E is always a positive value. So Y equals, and then we absorb just like I did before. I'll show it one more time where we separate this out and then we go, hey, that's really just a constant right there. And we turn it into the mega constant and we're going to think of this as Y equals a constant times E to the KT, right? So pretty much you don't have to do this process every single time. If you pretty much just memorize that when you know the rate of change is directly proportional to the amount you have, then you're going to memorize, hey, it's exponential growth and there's a constant in front. This C is always the initial amount. It's kind of like your initial condition. And we've done a little bit with exponential growth and decay before. All right, so let's take a look at example 5, calculator permitted. Our bacteria is going to increase from 400 to 1600 in 3 hours. And we're going to assume that the rate of increase is directly proportional to the population, and we want to find an appropriate equation to model the population. Well, here in A, we're not going to write the differential equation, separate it, and solve it. We're going to say we know y equals c e to the kt. Okay? C is going to come from our initial amount. We're pretty much going to assume that this 400 is going to be your initial amount. So y of 0 is going to be 400. And then we're going to assume y of 3 hours later, is going to give me my 1600 in this problem. Once I know this, you pretty much know that this is an initial condition, which is going to give you information about C. C is going to be 400. See how easy that was? So now I've got y equals 400 e to the kt. And you go, wait a minute, I still have a constant to find. I still have k to find. Well, that's what we use this second condition for. So this condition we're going to use to find k. And so basically I'm just going to plug it in and solve for k. 1600 equals 400 e to the kt. Divide by 400. So 400 equals e to the kt. And you know a little bit of your log solving. Natural log of 400. Oh, I forgot to plug in 3 for my t. So this should be 3. That should be 3. So natural log of 400 equals 3k. And so k is exactly natural log of 400 divided by 3. Okay? And a lot of times when you're doing this, a lot of times they say it's better to solve for e to the k, because watch what happens. Now I'm going to put this back in. Y equals 400 e to the natural log of 400 divided by 3 times t. Now, let's think about this because go a little bit of log properties. That if I were to have here, I basically have 1/3 natural log of 400. And then the property says if you have a number in front of a log, you can always move it inside as a power. So this is really natural log of 400 to the 1/3. And when I do that, I basically have this idea that this problem, using my log properties, is going to be 400 e to the natural log of 400 to the 1/3, parentheses, and then that whole thing is being raised to the t. And e to the natural log of 100, what happens to the e and the natural log? They cancel out. So you basically end up with is 400 times 400 to the t over 3. And that's what they're saying a lot of times. It's a little easier. Look at how nice the problem is because we can usually use that to calculate things a little faster and you don't have to have an e. Okay. Part B up here, just to finish this problem out, you want to find the number of bacteria at the end of 6 hours, so I pretty much just need to find y of 6. Using this model or that model, it's not going to matter. It's going to be 400 times 400 to the 6 over 3 squared, okay, which is 400 cubed. Type in your calculator and get your answer for that. So that will tell you the number of bacteria. If this was an AP question and free response, make sure you answer the question thoroughly. And so the number of bacteria after 6 hours is 400 to the cubed bacteria. All right, and then we can walk away from that one. All right, let's take a look at example 6, and then I'll probably leave a lot of these for you to do on your own. All right, so calculators permitted. We're given that this radium loses its mass at a rate directly proportional to its mass. So that's your dy dt is directly proportional to its mass, y, which is that, hey, this is exponential growth. So we pretty much know that in solving that our formula is going to be y equals c e to the kt. See, memorize, you don't have to do the whole solving the differential equation thing, because these are pretty standard. And once I have this, and we know that its half-life is 1590 years. So what that basically is telling you, that at y of 0, you can think of it as having, say, 1, because that will make c easy, and then 1590 years later, you will have half the amount that you had. So that's what I'm using this half-life for here. So this is going to give me my c equal to 1, so I can plug that in right there. All right, so this is all still part of A. So y equals e to the kt. And then we know that our 1590 years later is a half. So we use the second piece of information to find k. What that's going to do for me is that e to the 1590k is going to equal 1/2. And this should get almost, you can almost memorize what k is going to end up being. It's going to be the natural log of 1/2 divided by 1590k is going to be divided by 1590. And then again, remember the whole version of this is if you actually plug it back in, we usually take that 1/2 and we put this 1 over 1590 back on the inside as a exponent. And so when I go to plug it back in, my equation is e to the natural log of 1/2 to the 1 over 1590, and that's all to the t, which looks really complicated, but remember this and this cancels and it ends up being 1/2 to the t over 1590. So you can kind of skip this part and go straight to here, because you can pretty much memorize, hey, it was a half-life, and divide by the time that it takes to get there. So these are pretty simple. These are almost pre-calculus problems. Part B is you want to find the mass after 1,000 years. So you're basically doing y of 1,000, and you plug that in 1/2 to the 1,000 divided by 1590. I will leave that for you to put in your calculator. And then they want to know, when will the mass be reduced to 30 milligrams? So for part C, it's just working the other way. You want to know y of what time is going to equal 30 milligrams. So you pretty much just set it equal to your equation, and then you are going to solve. Let's do a little review of solving here. If I want to solve this, I like to switch it. You can do the natural log of both sides. That's the most common method. Of course, I haven't left myself enough room. I'm going to pause and cheat and give myself, all right, so through the magic of I can pause and stop. We get to here. Most common method, take the natural log of both sides. When you take the natural log of this side, the exponent moves in front. So t over 1590, natural log of 1/2. We're solving for t. Divide by natural log of 1/2. And then multiply by 1590, and we would type that into our calculator to get our approximate answer, and make sure you answer the question. The mass will be reduced to 30 milligrams after, and then fill in your your amount that you find from typing that into your calculator. All right, so these are fairly straightforward problems that you're going to be looking at. All right, let's take a look at example 7. Okay, I just realized I made a mistake back here, arithmetic mistake, which is always bad. You had a calculator permitted. I was trying to rush through it with no calculator, but 1600 divided by 400 is 4, not 400. So let's take the zeros out of each of these little answers. Hopefully you caught that while I was doing it. So this is just ln of 4, which ends up being 4 to the t over 3, okay? So that way you can go ahead and finish that problem up. But just all of a sudden I was like, oh, I have a slight mistake there. All right, so now let's go back to where we are, which is working on example 7. All right, so looking at example 7, a lot of these problems, we actually don't even need calculus to do them. We've got the amount of oil. It's going to decrease at a continuous rate of 10% per year. All right, you can either take a look at the problem and go, hey, it's the continuous rate, 10% per year. We know it's going to be CE to the KT. You can kind of assume that you're going to start with 1 or 100% e to the KT and use that for your initial condition. And then go, hey, I lost 10% per year. Now, this is where you have to be careful. If I lose 10% at the end of the first year, how much will I have left? 90% or 0.9, given that I started with 1. So if you're going to do that, then you just simply go 0.9 equals e to the k times 1, and k equals the natural log of 0.9. Now you don't even need to go through this part of it, because you can basically, if you think about your Algebra 2 pre-calculus, and we did this back in trig, you know that you can basically go, hey, I started with 100%, and my base is going to be how much I'm losing. My continuous rate is 10% per year. The base of your exponential function is equal to your 1 plus your r. And your r in this case is going to be 1 plus negative 0.1% because I decreased by 10%, which is going to give me a base of 0.9. And I get to that 0.9 in a year, so this would end up being t over 1. If it had happened in 2 years, it would have been t over 2, and so on and so on and so on. And remember that this 0.9 is what is your e to the k. So a lot of times we come directly to this right here. And then to answer the question, so this is the model for the problem that we're talking about. And then I want to say, when will the output fall to 1/5? So for the second part of this problem, I just go, well, when is the 1/5 equal to 0.9 to the t? And then we simply solve natural log of 1/5 equals t natural log of 0.9. So t is natural log of 1/5 over natural log of 0.9. So these end up being fairly simple problems for you to work with. You'll see some of them in the multiple choice section, and you're like, hey, this isn't calculus, because it's not really. You can answer this all with pre-calculus. Population of fruit flies grows in proportion to the number of fruit flies in the population. Right there is your key. We know it's y equals CE to the KT. We know that there were 100 flies after the second day, okay? Or if you prefer, your y of 2 is equal to 100. And we know that there are 300 flies after the fourth day, and y of 4 is equal to 300. All right, so we do have, but the thing that we don't have, which we might cry a little bit about, is we don't have our initial condition. We don't have at time 0. However, we can still do this problem. We basically need to find two constants, c and k, and I have two pieces of information. So all you have to do is create a system. Plug in your 100 equals CE to the 2t, and then plug in your 300. So 300 equals CE to the 4t. Now, the interesting thing about these, and instead of doing substitution, like trying to solve for 1 and then substituting, The neat thing, and we did this in your pre-calc classes, is basically all you have to do is think of it as a ratio. 300 over 100 would be equivalent to CE to the 4t over CE to the 2t. Now, if I set up this ratio, then very quickly I go, oh, wait a minute, these have the same base. My exponent rule says when I divide like bases, you subtract your exponent. So this is e to the 2t, 4t minus 2t, equals 3, and then right there I can solve for t in this system. So natural log of 3 divided by 2 equals e, or another version, natural log of square root of 3, or 3 to the 1/2. Let's do 3 to the 1/2. 3 to the 1/2 is going to give me my, I need to erase this. This is going to be equal to t. And then we plug it back in, and so we have, like I said, I plug it back into this top one, 100 equals c times e to the 2 times, plug in your t, natural log of 3 over 2, which 2's cancel, e's cancel, hey, 3c equals 100, so c equals 100 thirds. So our model that we can basically look at is going to be y equals 100 thirds, and then we can either do e to the, oh, you know what? I plugged in 2, this should be k. I'm trying to rush through this, and I'm just writing a couple things down wrong. Let's just change these all to k's. All right, so this would be e to the k. We can leave it as natural log of 3 to the 1/2, and of course this whole thing raised to the t, or we can simply reduce it down to our 100 thirds, and then this would end up being, the e and the natural log cancel out, 3 to the t over 2. All right? And so you can kind of then use that model to answer the next question, how many flies were in the original population? We've got that. And make sure you write the sentence. So that's pretty straightforward. Now, I'm going to come in, and I think we've done enough of these that I can leave example 9 for you to do, and I can leave, and that's it. So we have one more example, which is a free response. So I would like you to finish this up, and then we're done with the notes. The worksheet on separable differential equations is again going to be optional. You must finish this, and then you can do the optional worksheet. The key is online, and you can use that to help you prepare.